Hi, everybody. Today we're looking at Lesson 2, Population Samples and Hypotheses. So we have some definitions here, and I would suggest, you have your notes out and you have a highlighter out. We have a population is the collection of all data, such as responses, measurements, or counts that you want information about. And a sample is a subset of the population. So it's not always practical to be able to poll an entire population. You may just want to look at a sample. So, in other words, if we wanted to know how many seniors in high school across America drive their own car to school, we may not be able to reach every single senior in America and ask them that question. So maybe we would just poll the seniors at Mendham High School and see how many of them drive their own car, and then we could draw a conclusion from the sample about the entire population. A census consists of data from an entire population, but unless a population is small, it's usually impractical to obtain all the population data. In most studies, information must be obtained from a random sample. It's important for a sample to be representative of a population. When the sample is not representative of the population, the conclusions may not be valid. So we have some examples here. We're looking to identify the population and then identifying the sample. In the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them own at least one pet. That should say one. All right, so what is the population? All right, in this case, the population is all adults ages 18 and over. And what is the sample? In this case, the sample is the 2,184 adults in the survey. All right. If we were to describe the sample, in this sample, we have 1,328 adults that own a pet, and the rest of the people do not own the pet. You don't have to write out describing the sample. All right, let's take a look at the next one. To estimate the gasoline mileage of new cars sold in the United States, a consumer advocacy group tests 845 new cars and finds they have an average of 25.1 miles per gallon. So the population here is all the new cars sold in the US. All right. And the sample is the 845 new cars that were tested. All right, pretty easy, right? Now, we've got population and a sample. We are going to be talking about how to describe a population or a sample. If we want a characteristic about a population, we're going to use the word parameter. Starts with a P, right? Population, parameter, they both start with a P. If we want to describe a characteristic of a sample, we're going to use the word statistic, right? Starts with an S. Nice and easy. Because some populations are too large to measure, a statistic, such as a sample mean, is used to estimate the parameter, such as the population mean. So we're going to take a look at some examples where we decide, do we have a parameter that's a characteristic of the population, or do we have a statistic, a characteristic of a sample? So for letter A, for all students taking the SAT in a recent year, the mean math score was 514. Is the mean score a parameter or a statistic? Right now, because we're talking about all the students, that means that we're talking about the entire population, All right. So this characteristic is a parameter. A survey of 1,060 women ages 20 to 29 in the US found that the standard deviation of their heights is 2.6 inches. Is the standard deviation of the heights a parameter or a statistic? Right. Because we're looking at a specific group of women, a sample of women, right? So we have a sample of women. We know that we're talking about a statistic. We're not talking about all the women in the United States ages 20 to 29. We're talking about just 1,060 of them. All right, at this point, I would suggest you pause the video and try to do the practice problems here, and then, get it going again when you're ready. To estimate the retail prices for 3 grades of gas sold in the US, the Energy Information Association calls 800 retail gas outlets, records the prices, and determines the average price for each grade. Identify the population and the sample. Right, so the population in this case is all gas outlets in the US. And the sample is the 800 retail gas outlets that were called. Whoa. All right. Number 2, a survey of 4,464 shoppers in the US found they spent an average of $407.02 from Thursday through Sunday during a recent Thanksgiving holiday. Sounds about right. Identify the population and the sample. So in this case, the population is all shoppers in the US. And the sample is the 4,464 shoppers that were surveyed. The survey found that the median salary of 1,068 statisticians is about $72,800. Is the median salary a parameter or a statistic? All right, so in this case, we're talking about a survey, right, of just these statisticians, just about 1,000 people. So since we're taking a sample with this survey, we know that we're talking about a statistic. All right, so I'm going to write statistic. All right, the median is based on a subset of the population, or a sample of the population. Okie dokie, keeping it moving here. The mean age of US representatives at the start of the 113th Congress was about 57 years old. Is this mean age a parameter or a statistic? All right, so we looked at all of the US representatives in the 113th Congress. So since we're talking about everybody, this is a parameter. It's a characteristic of the population. All right, we said the mean was based on all US representatives. Just say reps. Okay. Moving on. Analyzing hypotheses. In a statistic, a hypothesis is a claim about a characteristic of a population. So here are some sample samples of what we mean, right? Some examples. A drug company claims that patients using its weight loss drug lost an average of 24 pounds in the first 3 months. That is a claim. A medical researcher claims that the proportion of US adults living with one or more chronic conditions, such as high blood pressure, is 45%. Okay, they claim that that's true. To analyze a hypothesis, you need to distinguish between results that can easily occur by chance and results that are highly unlikely to occur by chance. Right? One of the ways we can test a hypothesis is to perform a simulation. When the results are highly unlikely to occur, the hypothesis is most likely false. So we're looking for something that is likely to occur to say that the hypothesis is most likely true. All right? So we're going to look at an example here where we do a simulation and we're going to analyze the hypothesis. So we have a 6-sided die that we're going to roll 5 times, and every time we roll the die, we do not get an even number. All right, that's pretty strange. We rolled it 5 times, half the numbers on a die are even. I should expect at least one time I'm getting an even number. So the probability that this happens is 0.03 or 3%. So you start thinking maybe this die favors odd numbers. The die maker claims the die does not favor odd numbers. What should you conclude when you roll the die 50 times, or when you roll the die 26 times, or when you roll the die 35 times? All right, so we're going to take a look at that. The maker's claim or hypothesis, first of all, our hypothesis in this case is the die does not favor odd numbers. All right, this is the same as saying that if you kept rolling this die over and over and over, in the long run, you would get about 50% of the time you would get odd numbers. Now, to analyze the hypothesis, we first simulate the rolling of the die, repeatedly drawing 200 random samples of a size 50 from a population of 50% ones and 50% zeros. All right, so what does that mean? Here's an example. This picture right here is explaining what happened in this simulation. The x-axis, right, is the proportion of 50 rolls that resulted in odd numbers. And then this part right here is our relative frequency. That's how many times it occurred. So right now you're probably still a little bit confused. I think this diagram is a little bit confusing. The best way now to really help you understand it is we're going to look at some examples. So it says, what should you conclude when you roll the die 50 times and you get 26 odd numbers? Okay, well, first of all, let's see here. 26 divided by 50. If we put that in our calculator, we're going to get 0.52. All right, so 0.52. Let's go find that on our histogram here. Right there is 0.52. And if we look at the frequency at 0.52, we get a value of 0.16. It occurred a lot, okay? Because it can occur a lot, because our relative frequency is high, we are going to conclude in this case that the maker's claim is most likely true. So, most likely true. Okay, we have a very high frequency in that case. All right, let's look at another one. What should you conclude when you roll the die 50 times and you get 35 odd numbers? Okay, let's see here. 35 out of 50. 35 out of 50 is 0.7. All right, I'm going to use a different color this time. All right, so here's 0.7, and we actually have a frequency of 0. It never happened, okay? So this one is very unlikely to happen. If this was the scenario, right, for you, that you rolled this 35 out of 50 times, right, and you got odd numbers, that's very unlikely to happen based on our relative frequency relative frequency chart. So this one would be most likely false. Very unlikely. Right. Now there are two practice right here. I would say pause, right? Try it out and then restart the video. For the practice number one, what should you conclude if you roll the die 50 times and you get 24 odd numbers? All right, 24 out of 50, that gives us 0.48. Let's go find that on our chart. Here's 0.48 right here. And if we look at the relative frequency, that's almost 0.12. So I would say that's about 0.115, almost 0.12. Right, so that's pretty high up there. That was a pretty significant frequency on our chart. That's one of the higher bars. So I would say in that case, most likely true. And then the last one, what should we conclude when we roll the die 50 times and we get 31 odd numbers? Okay, 31 out of 50, that gives us 0.62. Let's find that on our chart. Right here is 0.62. That's just a little bit above 0.02 because this is 0.02 right here. So I would say this is about 0.025. And that's a very low frequency on our chart. So in this case, I would say most likely false. So this example really is meant to give you a sense for how to take a bar graph that is representing a simulation and trying to understand whether or not you would prove a hypothesis true or false. This one's a little tricky to read, this diagram. You have to really think about it. I think you have to be careful that you take the time to really understand what the diagram is demonstrating. Now, next up, you'll be doing some practice. This is going to reinforce everything we learned in this lesson. There's a lot of vocabulary here, not much math, which I think some of you will like. So I hope you enjoyed it. Thanks for watching.